We're going to start now the afternoon section. And our first lecturer is Professor Horatiu Nastase, which is a member of the House. However, he was born in a different country. He's from Romania. He graduated in the University of Bucharest in 1995. And he's a member of IFT since 2010. That's right. And he's going to speak about something that you probably heard, which is the AdSCFT correspondence. So please.
Thank you. Thanks for inviting me to speak to many students, which is always a great pleasure because one hopes that this will inspire you to follow a career in this field. So today I'm going to talk to you about basically my main research area, which is called the AdS-CFT correspondence. And it's a way to relate gravitational physics, so physics that involves gravity on one side, and physics that doesn't involve gravity on the other. So I will first introduce to you what the problem is. Then I'll tell you that within string theory, we can describe this AdS-CFT correspondence, although by now it's kind of independent of string theory. And then I'll tell you that we can use this correspondence to describe things in particle and nuclear physics, in condensed matter, and in cosmology. All right, so first of all, a bit of motivation about string theory itself. If we look at the evolution of physics throughout the past centuries, we see that there is a tendency to go towards substructure and towards unification. If you look, first we had the idea of an atom, something that all matter is composed of. And in the modern times, John Dalton, about 200 years ago, thought of the precise description of atoms. Then people dug deeper and they saw, well, atoms are made of nucleus and electrons, as proven by J.J. Thomson. Then even further, people saw that the nucleus itself is made out of protons and neutrons, particularly the experiments of Chadwick. Then the nucleus itself is shown to have substructure, namely to be made up of quarks. To be made of quarks, first thought of by Gell-Mann, and then proven in experiments at SLAC. And on the other hand, if you look at the way people describe nature, two common phenomena were electricity and magnetism, associated with electric and magnetic force. And then Maxwell showed that they are in fact manifestation of a single type of force. And then later on, if people introduced also a common description in terms of electromagnetism and the weak interaction that are responsible for some nuclear interactions. And that came to be known as the electroweak interaction, theorized by Glashow, Salam, and Weinberg, made more rigorous by 't Hooft and Veltman, all these people getting Nobel Prizes, and then finally experimentally proven. Well, there's one more nuclear force, the strong nuclear force, and there are many attempts at a common unified theory called grand unified theory, GUT. All in all, then, we look at matter and the forces that act between them, and we see that there is a common, well, kind of unified description. They're still lacking this GUT, but people believe that something like this must be true. And the whole description has a symmetry invariance that is described by the group SU3 for the strong interactions and group SU2 cross U1 for the electroweak interactions. And using this symmetry, we can group the fundamental particles that we see in groups of quarks, leptons, and Higgs. And all in all, these groups of particles with these symmetries make up the standard model of particle physics. So given this idea of, given this observation that physics evolved towards substructure and unification, it's natural to ask whether this can continue further. Well, the question of whether there is substructure for the moment seems to be answered in the negative. There doesn't seem to be any new evidence of further substructure. But for the issue of unification, we have a problem that gravity seems to stand apart. Gravity seems to be somewhat different in that gravity is associated, the common description of gravity is associated not with some interactions related to some particles and some unification groups, but rather to the geometry of space-time. So that seems different. So string theory, then, is an attempt, the only consistent attempt so far, to describe in a unified way the standard model of particle physics and gravity within a quantum theory. Now, if we want to see when, at what kind of energies does that happen, we can just use dimensional analysis and find that because this is supposed to be a quantum theory involving gravity, the natural scale will be the quantum gravity scale, which is about 10 to the 19 GeV, which is about 15 orders of magnitude beyond what is obtained today. So it's very, very far. I mean, it's not even clear that we will one day be able to reach such energies. So then that means that it's very hard, whatever we do, it's very hard to test directly, to make predictions. Well, we'll only make what I called here in quotations postdictions, meaning that we kind of try to explain all the things that we see, but that's not so impressive maybe. I mean, physics always evolves by making predictions. However, a new point of view arose in 1997 due to Juan Maldacena, an Argentinian physicist working in the US, and that is the so-called AdS-CFT correspondence. So, this AdS-CFT correspondence then corresponds to taking a certain limit in string theory and obtaining two dual or equivalent descriptions, one involving gravity and the other being without gravity. I'll try to describe for you what that is. But the point about this is that instead of trying to predict new things, things that we didn't already know, this AdS-CFT correspondence makes predictions for known theories, like QCD, the theory of strong interactions, meaning that the only thing we're trying to do is to calculate things that we weren't able to calculate otherwise. That is that strong coupling where there is no perturbation theory that can help us. So this being a duality between two different descriptions, we have a mapping. And the reason this duality is useful is because it maps strong and weak couplings, curved space with flat space, and also it turns out it relates bulk with boundary, meaning a 2 plus 1 dimensional space-time with a d plus 1 dimensional space-time with a d-dimensional space-time. And also, as I said, gravity with just fields without gravity. And we will try to apply this in both directions. We will use gravitational physics to describe nuclear and particle physics, and the same gravitational physics to describe condensed matter. And reversely, we will use field theory to describe cosmology, which is the most interesting thing that we can do within gravitational physics. There are other things about black holes, but I'll not describe those. All right, so what is string theory? As I said, the basic definition is the idea of unification of various kinds of particles and interactions. And that is also a theory, a quantum theory of gravity, without problems. We could always write a simple quantum theory of gravity, but if we write this simple quantum theory of gravity, we have an apparent problem. There's an interaction between gravitons, so h mu nu here represents a gravitational perturbation or graviton. So there's an interaction, for instance, between 4 gravitons with a coupling that goes like Newton's coupling times something that goes like the energy squared. So that means that this coupling goes to infinity when the energy goes to infinity. And that is bad for various reasons, but you can think simply that, well, you shouldn't be able to see large energies. We should only see a theory about the lowest energies. And here it seems like the largest energies are the most important. And these kind of infinities that appear are called non-renormalizable infinities, or infinities we can't get rid of. Then, as I said, the natural energy scale at which we would see the new physics is the energy of quantum gravity, which itself is found by dimensional analysis. We know that it's supposed to be a relativistic quantum gravity theory. Relativistic means C has to appear, quantum means h bar has to appear, and gravity means g Newton has to appear. And there's a unique combination of them with dimensions of energy, which is about 10 to the 19 GeV. So at these energies, string theory says that all the known matter particles, leptons, quarks, the Higgs, as well as other exotics, things that are not described within this set, as well as force particles or gauge bosons, are all in reality just tiny vibrating strings. So if we had an hypothetical microscope, of course such thing doesn't exist and it's only an idea. If we had a hypothetical microscope, we would see, instead of what looks to us like a point, just a tiny oscillating string. And then why are there different kinds of particles? Well, because this string has different vibrational modes, right? I mean, well, I don't have a piece of string with me, but imagine a closed string, and then there's an oscillation mode up and down, for instance. There's one in the plane. There's another one in the plane. There are various kinds of oscillation modes. Now, if you also think that, in fact, as we'll see, there are more dimensions, you see there are plenty of oscillation modes available, as well as so not just the fundamental frequencies, but also their higher modes. Now, why is it that a string theory is also a quantum theory of gravity? Well, if we take such a string and we spin it around, we just give it an angular momentum, then we can find the classical relation between this angular momentum or spin and mass or energy squared of the string, which is linear. So J is proportional to m squared. The same relation holds in a quantum theory, just that in a quantum theory, these are not continuous variables. They're just take discrete values. And in particular, if you put m squared to 0, corresponding to a massless or long-range particle for interaction, a force particle, then you get that the spin J is equal to 2. And something with a spin 2 means that it has a quadrupole kind of oscillation. And well, as you know, electromagnetism is a dipole. You can emit electromagnetic radiation from an antenna, which is a one-dimensional thing. But you cannot, but you can emit gravitational radiation only from a quadrupole, something that is three-dimensional intrinsically. So the only thing that we know that is long range, has spin too, is a graviton. So that means that really we have a graviton in the spectrum of the string. So string theory, the quantum string theory is a theory that includes quantum gravity. And also all the possible Jn, Mn doubles, so these sets Jn and Mn, correspond to different kinds of particles. And since this is an infinite line, even when it's discretized, it still remains an infinite number. So we have an infinite number of different kinds of particles. If you want to make an analogy, think of the hydrogen atom, and then you know that in the hydrogen atom you have quantum numbers, angular momentum, spin projection, and energy. And those correspond to different states of the electron inside the hydrogen atom. Choosing these sets corresponds to different states of the string within the vacuum, and correspondingly these are called different particles. Now one detail is that for quantum mechanical consistency, the strings have to live in 10 or sometimes in some sense 11 dimensions. However, we only see 3 plus 1 dimensions, which means that the extra dimensions must be in some sense curled up, forming some compact space. Compact space means something like a sphere. This is known as Kaluza-Klein compactification. And one of the nice things is that then this compact space has symmetries. Think of the sphere as having rotational symmetry. And the internal symmetries of particle physics, like this SU3 cross SU2 cross U1 of the standard model, are just symmetries of the compact space. So they become just geometric. There are no free parameters in string theory. There's nothing that needs to be tuned to obtain something sensible. And so this is called a theory of everything, sometimes in trying to make fun of string theory. But the point is that really, because of the richness of the theory, you can describe all sorts of phenomena, some of them in the real world, but some of them just abstract. And we're, in fact, interested in this abstract description. And the physical parameters and symmetries come just from solutions. What technically would be called vacua of the theory. And as an example, that's not really physical, but just a simple way to understand this. Imagine that the radii of the extra dimensions satisfy an equation like this. Then all Ri, which are integer numbers times this Li, are different kind of vacua, that different solutions that would correspond to different potential universes. So that's the kind of, that's really what we mean. So then physical parameters and symmetries appear from these solutions. There's a huge amount of would-be vacua. People argue about the numbers. I saw some people even saying this, number that's even hard to imagine. But most are not true vacua. And in any case, the standard model was not even obtained yet. So there's an issue there. Another point is that while strings are fundamental objects in this theory, when the intrinsic coupling of the string theory becomes large, we obtain that the strings kind of fatten up and become membranes. And also, we find soliton-like objects in the theory that extend in p spatial dimensions. that are, you can think of as some sort of fluctuating walls. So we have all these all kinds of beasts in the theory. So one important point is that at energies that are kind of low, string theory becomes just a classical theory of gravity, supergravity in this case, but classical theory of gravity. And finally, a last point I want to make about the string theory is that even though normally we consider compactification, we could also consider the idea of a brane world, meaning that particle physics lives on this kind of fluctuating walls. Instead of living in the whole space, they live on just some walls in the theory. All right, so what is the AdS-CFT correspondence? As I said, Maldacena proposed to use string theory as a tool rather than a fundamental theory, as a tool to solve known but strong coupling theories. So originally he thought about it as obtaining a toy model for QCD, the theory of strong interactions, so to describe particle physics. But later it was generalized to much more. And then we consider one of these abstract solutions. As I said, there's a huge amount of them around. And it doesn't matter that this is not related to the real world. We just consider one of these solutions. And the solution we're considering is called anti-de Sitter, 5-dimensional anti-de Sitter times 5-dimensional sphere, AdS5 cross S5. And then, when considering this solution, we obtain a duality, meaning we obtain a different non-gravitational description for this, that also has the property of being weakly coupled when this one is strongly coupled, and vice versa. And the alternative description is a 4-dimensional field theory living on such a wall, on such a D3 brane, a 3 plus 1 dimensional wall, that is just one of these objects existing in string theory. So we have a relation between this 10-dimensional string theory on AdS5 cross S5 and this 4-dimensional field theory on a fluctuating wall. So the fact that this is a duality means that all the physics in this AdS would-be universe is equivalent to the physics of on the D3 branes that is a toy model for QCD. I mean, formally we write the description as saying the partition functions of the two. Partition functions, like for standard thermodynamics, is some function that encodes all the relevant physics. So all the relevant physics on both sides is equal. And as I said, this relates a certain coupling in the field theory with, roughly speaking, 1 over the coupling in gravity. So that relates strong coupling with weak coupling. Now the strong interaction theory here is not QCD, but rather it's a toy model for it, known as N=4 Sperr-Mills, which is a theory that has no overall notion of scale. What we say technically is called conformal theory. This duality is also holographic. I mean, it has to be something non-trivial because we're trying to describe two very different beasts. They have different dimensions. One is a 10-dimensional theory, one is a 4-dimensional theory. And also one has gravity, the other one doesn't. So it's clear it has to be something non-trivial. And the map is holographic, meaning from the bulk to a boundary. And information is encoded non-locally, just like in a regular hologram. So if you have a hologram, so unlike a regular photo, in a regular photograph, you take a 3-dimensional object and you project it onto a plane, the photograph. But in a hologram, you don't do a projection. Every point on the hologram has information about the whole object, and every point on the object is projected onto the whole hologram. Meaning, in particular, if you are interested in experimenting with this, if you take a hologram and cut it in two, you obtain two holograms, not two hologram halves. Just two holograms of lower quality. So this idea of a hologram applies to AdS space that can be represented in what's technically known as a Penrose diagram by a kind of infinite cylinder. So this extends to infinity in up and down. But then the cylinder has a boundary at a finite radius. And this boundary is a representation of our four-dimensional space-time. So we and everything we know lives on this boundary of this cylinder, but we want to describe it as the physics inside the cylinder. So our world, our four-dimensional world, is in some sense a hologram of this AdS space. All right. So that is what the AdS-CFT correspondence is, roughly speaking. But how do we apply it? What do we gain from this description? Well, we'll start with what do we gain for particle physics and nuclear physics. As I said, the original description of Maldacena involved a toy model for QCD that is called n equal 4 super M mils. It's very simple, and in particular has no notion of scale. It's conformal. But it's in some sense too simple. So in order to describe something real, we need some improvement of this thing, what I would call a QCD hologram. But this is hard. So as always, we just do still a toy model, but a slightly better one. Two common ideas are, so one is to add a finite temperature to this duality. The temperature is something with dimensions, so that definitely includes a scale. The temperature is a scale, but it's a simple kind of scale. However, it turns out that there is some evidence for universality of quantum field theories at finite temperature. So that means just adding temperature, I can still use this n equal 4 super M mils. The other simple idea is just to put a blunt cutoff in AdS space, so just to take scissors and just cut a hole in AdS space. So AdS space was represented by this infinite cylinder. What I mean is I cut a smaller cylinder around the middle. That's my toy model for this QCD hologram. So the finite temperature is a variation of this second point where the cutoff is not so smooth, it's done in a specific way. But either way, this is roughly represented, as I said, by just cutting a tiny cylinder from the middle of the bigger cylinder. And now that we have this gravitational space in the form of the cutoff cylinder, we can describe states and properties of particles. And also we can describe heavy ion collisions creating what is known as a fireball that relates to properties of nuclear physics. So just to emphasize what I just said, we take this infinitely long cylinder corresponding to AdS space, and we cut off a smaller cylinder in the middle. That's a rough approximation of what we expect would be a good description, good gravitational description for QCD. In the real world, of course, what happens is it depends how you cut. So it depends very much on the details near this cut, near this end of the space in the middle. Okay, so I tried to draw here a section of this. So the boundary is fixed, but then we're cutting somewhere here. And then how we're cutting near this region that those details are what defines more precisely the QCD hologram. So just to see how is it possible to get something like nucleons, I mean protons, neutrons, things that made up the real world, out of this gravitational description, one can prove that by cutting off this cylinder in the middle, if I measure the amount of time it takes light to go from this boundary to this boundary, it's a finite time. Now this is kind of bizarre because you say, how is it possible for light to take a finite time to go to infinity? But this is one of those things about general relativity, the theory of gravity in curved space, that is hard to imagine. You just have to calculate and see that it's like this. Anyway, so the point is, from the point of view of signals propagating, like light, these two boundaries of the space at infinity and in the middle are a finite time away. So if you think about that, you think of this thing as really like something like a drum. I mean, this kind of looks cylindrical. I even cut it off here and here, right? So think of this cylinder with a smaller cylinder cut off in the middle as a physical drum, and then think of yourself as just starting to bang it on top, which means you propagate information throughout the space, right? And the information bounces off from the boundaries and comes back. And then what you create? Stationary waves, right? You create stationary waves within the drum. So exciting the space creates stationary waves of given frequencies. So those are some resonant frequencies. Fn is equal to n times the fundamental frequency. And then, so you think of this in this QCD hologram, and then these resonant frequencies correspond to the given masses of excitations of this theory, right? So the masses are hc squared times the frequencies. And then these masses corresponds to the masses of nucleon-like particles within QCD, all right? This is why we were able to obtain something like nucleon masses within the theory, and by extension, nuclear physics. Now, the catch is, of course, that, as I said, we don't really know the details of the QCD hologram very well. We don't know exactly what happens near this wall in the middle. In here, as I said, in this region, we don't know exactly what happens. And by an analogy, if you don't really know the shape of the drum, then you can't calculate precisely the frequencies, the resonant frequencies, which translated to us, that means we can't really calculate precisely the masses of the nucleons, or nucleon-like particles, okay? So that's why we can't really, for the moment, give good comparisons with nuclear physics, just some approximate ones. All right, so how do we calculate something interesting about nuclear physics? As I said, finite temperature is part of the equation. In order to obtain something like the QCD hologram, we could put finite temperature to n equal 4 spamils. And then, as I said, there's some sort of universality. And this is obtained in heavy ion collisions at Brookhaven and the LHC, where we collide nuclei, heavy nuclei. And then what happens is there's a hot state of matter that forms with a very large temperature that corresponds to strongly coupled quark-gluon plasma, which then decays, so it's this kind of ball, fireball if you want, that then decays by emitting tens of thousands of particles, mostly the lowest particles available in QCD, which are pions. But if you're mostly emitting pions and you moreover emit on a thermal black body spectrum, which as you know is fixed, that means you lose information. So the loss of information about what kind of particles collided is equivalent to the apparent information loss in a black hole, meaning that if you have a black hole, you throw stuff in, books, spaceships, planets, whatever, and only radiation comes out. Only black body radiation comes out. This is, roughly speaking, the idea of the black hole information paradox. And we see something similar here. So in this case, this fireball is the equivalent of a black hole and can be thought of as a kind of a perfect oven in the theory. So let me say a few more words about that before coming to the picture. So first of all, what is a black hole? Well, the name says it's a hole in space that's black. So black means that not even light can escape from it. However, Hawking showed that even though it's black, but still it emits radiation at a very low temperature, a temperature which is proportional to 1 over the mass. So as you can see some numbers here for the black hole with the mass of the sun, you get the temperature of 10⁻⁸ Kelvin, extremely small. So that means, as I said, the black hole is like a perfect oven, that everything falls in and gets burned and only radiation comes out. So the black hole is a perfect oven in a gravitational theory. So think of this the following way. If you have an oven and you throw logs in and then you burn them, you look inside the oven and you see the logs burning. So you see information about what you've thrown in, right? But now if you think of the idealization of this, that it's in some sense, it burns so thoroughly that you can only see heat and you don't see the information coming from the logs directly, then you have an image of what a black hole is supposed to be. And there's, of course, the detail that for the oven, there's always a boundary, the oven itself, whereas for the black hole, there's no, the boundary of the black hole is the oven. So there's an idealization further. So then, by this analysis, I say that if I put a black hole in AdS space, that should correspond to putting the four-dimensional theory at a finite temperature through this idealization of black hole being a perfect oven at some temperature. But also it means that a gravitational collision producing a black hole in the QCD hologram is equivalent to this collision producing a fireball. So there's an analogy between these black holes and these fireballs. As I said, there is some universality in the hologram spaces with black holes that corresponds to this universality in finite temperature plasmas I mentioned as well. What does it mean, this universality? Well, one example of the universality is that these hologram spaces with black holes, for them you can calculate shear viscosity. I mean, really viscosity in the sense that you take two objects and you try to make them go in opposite directions, and there's a force opposing that, right? And then also you can calculate entropy density, and the ratio of these two in most hologram spaces is a fixed number, 1/4π, that also turns out to be a kind of lower bound. In most systems, this is bounded by 1/4π. So in some sense, this system is the least viscous of all. Now, one implication that is still not clear that I proposed is that the LHC itself should see black holes corresponding to, we should see these sort of fireballs corresponding to black holes in the dual space. And moreover, they should see fireballs made up of only pions. Now, I say LHC because what has been observed is really in heavy ion collision. I mean, in the LHC itself, the ALICE experiment looks at heavy ion collisions, but the main experiment looks at PP collisions, PP bar collisions. So I claim that, in fact, one should also see in PP bar. It's just a little bit more complicated for many experimental details. And one interesting thing related to the AdS-CFT correspondence, it is that there was a model for what happens when you collide two nucleons at extremely high energies, written already in 1952 by Heisenberg, which claimed that you can describe this with a simple Lagrangian written here called the DBI Lagrangian. And you can obtain and revise this model in AdS-CFT, as we did a few years ago with Kobe Sonnenschein. And this comes really naturally from the AdS-CFT description and predicts what I said here. Another application of the AdS-CFT correspondence is to condensed matter. I talked about finite temperatures strongly coupled field theory, and that, of course, has one application, this strongly coupled QGP. But the other obvious thing to do is condensed matter. Condensed matter always has finite temperature. And in some cases, it can be at strong coupling. So from this, you gather that condensed matter should be dual in some cases to some black holes living in the AdS space, or QCD hologram. And phenomenological applications of this AdS-CFT go under the name of AdS-CMT. What it means is you cook up a hologram space, a gravity dual so-called, whose field theory dual should have, according to the AdS-CFT rules, have some given properties that you like. One example that has been done is the so-called holographic superconductor found by these people that is supposed to describe type 2 high TC superconductivity, which is strongly coupled. And in this case, you know that there should be a background that's approximately of AdS type, because the theory near the superconducting phase transition is conformal. You know it should have a gauge field or photon-like object, because by the AdS-CFT rules, this is mapped to a current, and we should have a charge current. Superconductivity is related to some symmetry breaking, and that amounts that we should have some, in the gravitational description, we should have some operator that has a quantum vacuum expectation value. And we expect finite temperature, so in the gravity description, we should have a black hole. And the symmetry breaking is also mapped to the fact that the mass squared is not the standard mass squared, but is corrected by coupling to other fields, so it can become even negative. Anyway, sorry about these are kind of details that are harder to explain, but the point is once you put all these details in, you can cook up a hologram that has a black hole in it and describes very well some properties of superconductivity. Another example is the transport properties in strongly coupled systems. This is something that is one of the main interests in condensed matter to try to describe transport of various kinds. The common thing would be transport of charge and heat, so electric and heat conductivities. So just a reminder that the electric charge current and the heat current are proportional to the electric field. Oh, here it should have been EJ. Sorry, I forgot to put it. Proportional to the electric field and temperature gradient with some matrix coefficients. So this is a matrix relation between the two. The point is that if you take this black hole in the gravity dual and you look at a region, so-called membrane, near the black hole event horizon, you'll find that it has some fluid-like properties. So you could say there's a gravity-fluid correspondence, and also goes under the name of membrane paradigm. And so you can calculate the properties of this fluid, in particular transport like this, and then describe the transport in condensed matter in terms of this transport of the fluid. Another kind of application in condensed matter is the use of so-called dualities in field theory. The standard duality in field theory is the duality of Maxwell's equations between electric and magnetic fields, Maxwell duality. So this, if you make this change in Maxwell's equations, as well as a change between particles and monopoles, and coupling and 1 over coupling, then Maxwell's equations are invariant. There's a 3-dimensional version of that is a duality between particles and vortices, things that live on a plane, on a spatial plane. And perhaps not surprisingly, if you take this AdS-CFT duality that changes dimension, AdS-CFT duality maps this particle vortex duality into Maxwell duality. So this is on a boundary, on a 3-dimensional boundary of a 4-dimensional space, and then this relates it. And detail is these people, including myself, have shown that in 3 dimensions there's not just this basic object, but there's actually a duality web for theories with some kind of interactions, Chern-Simons type, whose basic object is a relation between bosons and fermions. And you apply it twice, you get either a boson-boson relation, that's this one, or a fermion-fermion relation, that's a relation between a Dirac fermion and a composite fermion. And you can apply it many times and get other things. Anyway, so the point is you can use the AdS-CFT correspondence to learn more about these field theory dualities as well. Okay, just to mention a few of the other things without explaining what those are, you can apply the AdS-CFT correspondence to spin chains in 1+1 dimensions, like the Heisenberg spin chain. These are obtained in certain limits of AdS-CFT, as shown by Bernstein, Maldacena, and myself. Then you can use integrabilities, which is a generalization of this idea by these people. You can use a large N quantum mechanical description for Majorana fermions that goes under the name of Sachdeva-Kitaev or SYK model that actually mimics black hole physics. You can find all sorts of properties like quantum properties like entanglement, complexity, and others from gravitational physics. So you can do all sorts of applications by now to various branches of condensed matter. And finally, let me say a little bit about applying the duality in the opposite direction to learn about gravity. This is still in development, and it's an application to cosmology. So cosmology is, well, obviously a gravitational theory. And the interesting part of cosmology, or rather I should say the one where there's more research going on, is the early universe cosmology, the cosmology at times very close to the Planck time, to where the energies and densities were very high. And in that case, gravity is much stronger. Because, you know, you might ask, well, nowadays gravity is by far the weakest force, right? It just happens to dominate because all the other forces are related to opposite charges and are screened. So, you know, electromagnetism is not dominant simply because there's equal amounts of positive and negative charges in all of us and everything around us. But otherwise it would dominate. Gravity is extremely weak as a force in the current universe. But if you go back in time all the way to close to the Big Bang, then everything was so much closer together that gravity was much stronger. And eventually we reach a point where gravity is of order 1, a force of order 1. So, is this relevant? Well, the usual model for cosmology is called inflation, and is one of these things that, you know, it's very beautiful and so on, but the only reason it was invented is because it's simple, because it's what you would do if you have effective field theory, where you assume that gravity is weak and you have a scalar on top of this gravity, the simplest kind of field that you can have, and then, you know, you calculate everything without knowing anything about quantum gravity. So this was a simple thing, and people are very happy that it matches all the data that we see. But if you go back and think, why is it that these people introduced this model? Well, simply because it was simple. You could calculate. There's no fundamental reason for this model to be valid. And so you could ask the question, is it not possible that gravity was extremely strong and you had some complicated model there? Well, yes, it turns out there's a large parameter space given observations that we can measure today. There's a large parameter space where it is highly possible to have strong gravity at the initial time. And then what do? Well, the thing is, you don't know quantum gravity theory, so you can't do much, people say. But with holographic idea, with the AdS-CFT correspondence, you can introduce a model where you can calculate. You can introduce what is known as holographic cosmology, where you simply say that you have this cosmological gravitational space, and there's a field theory dual to it, living at its boundary in some sense. Cosmology is 4-dimensional, as we know, and then its boundary is supposed to be something 3-dimensional. And then the simplest thing is to think, well, inflation works, so is it possible to have a strong gravity version of inflation? And the answer is yes. There's this holographic cosmology model. In particular, there's a phenomenological approach started by McFadden and Skanderis in 2009, and is based on also on this string theory picture where you have field theory living on this kind of solitons or brains. In this case, a D2 brain, something with 2 spatial dimensions and 1 time. And this gives a sort of domain wall type gravity. Now here I have some equations, but, well, if you don't know anything about gravity and cosmology, all I want to show here is that, so this would be the space corresponding to a cosmology. It's defined, this would be the space corresponding to a cosmology is defined by a factor A that depends on time, a scale factor A that depends on time. and there's a time t in here. Now, if you do a so-called Wick rotation that changes time to space, you can change this t into z, and then write this metric, which is a gravitational space of this type, of a domain wall type corresponding to a d-brane. So, so you can think of the relation between cosmology and the dual field theory as a Wick rotation of this standard type of relation between d-brane gravity and d-brane field theory. Also, by the AdSCFT map, the gravity plus scalar that are involved in inflation are mapped to the energy momentum tensor of the field theory. And then you can calculate the power spectrum of this gravity plus scalar, and moreover observe it in the cosmic microwave background radiation. This is one of the things that people take as a great proof of inflation, that you can match the experimental observation in CMBR with what you predict from inflation. And so you measure this spectrum given by this formula, 2-point functions of these fluctuations, never mind what that is. But this is related to the 2-point functions of the energy momentum tensor, which is given in here. And then I said, moreover, that McFadden and Candesis introduced a phenomenological approach. That is to say, you write a phenomenological three-dimensional theory, all the terms in the Lagrangian of the theory that you can imagine. And the one constraint you put is that dimensions in this theory are contained in momenta only through this effective coupling. And when you do that, you find that the fit to the data is as good in the standard model of cosmology, which is a cosmological constant called dark matter plus inflation. To be even more precise, you find that the chi-squared for the fit is this number, 124. I think this is for the holographic cosmology versus 823.5 for lambda CDM plus inflation. And when chi-squared is less than 1 between two different theories, it means the theories are indistinguishable experimentally. So the fit is as good and fixes the parameters of the theory. Moreover, one can, in principle, improve this because the fit, after the fit, you find that there's a region in the sky for which the corresponding field theory is not perturbative, so must exclude it from the fit. And people now are trying to put it back in. And finally, this year, myself and Skanderis have shown that the sort of classic puzzles of hot Big Bang cosmology that were solved by inflation in the early 80s are also solved in holographic cosmology. So together with a CMBR, I would say that they are as good as inflation. So there's a new paradigm extending inflation, meaning that inflation would be dual to a strongly coupled field theory, whereas this model is dual to a weakly coupled field theory. So there's a new paradigm that is as good as the inflation region. There's also top-down attempts to obtain something not phenomenological but well-defined, but there's some problems with it, and so on, that I'll not describe. So finally, to conclude, I'll say that AdSCFT is a tool to relate gravitational physics that comes a priori from string theory, but perhaps not necessarily, to field theory. We can solve non-perturbative field theory problems in particle and nuclear physics from perturbative gravity, and also solve non-perturbative problems in condensed matter from perturbative gravity, and reversely solve strong gravity cosmology from perturbative field theory. Okay, thank you.
So thank you very much, Professor Nastase, and we have time for questions.
So first, thank you for the talk. So just to get this straight, this AdS-CFT correspondence is a correspondence between an de Sitter universe in the bulk of something with conformal field theory on the boundary. Okay.
Well, so that was the original description of Maldacena. So in the original paper of Maldacena, he described AdS space versus conformal field theory and gave the relevant examples. But then throughout the time, I mean, more than 20 years since, people have tried to expand that further. So first, conformal field theory is not necessarily required. As I saw, the QCD hologram that I talked about is not conformal. It has as a scale. You can put that scale by temperature or just by hand, but the result is the same. So people have been trying to describe that. The problem is, as always in physics, when you go away from the toy model, you can no longer calculate things well. So with the toy model, you could do whatever, but without the toy model, you can calculate much less. So depending on how far you are from this original case, you can calculate more or less things. And then there's also this approach that I talked about in the case of both condensed matter and cosmology, which is a phenomenological approach. So in this case, you don't have a derivation of the duality. You just assume that if you set up your problem well and you use the same map as you had derived before, the holographic duality will still be true. So there's an assumption there. In the case of AdS spaces, the assumption is stronger. AdS spaces with stuff in it, the assumption is stronger. But in principle, the same assumption is also true outside it, which is the case when I describe this cosmological model. So there's an amount of uncertainty in these phenomenological approaches, but they're still believed to be valid.
Mm-hmm. So the second and possibly third question. In the Maldacena's case, what is the dimension of this AdS space-time?
Well, so the AdS is 5 dimensions, so AdS 5, but it's times a 5 sphere. Now, the thing is, there are two points. The first is that when you have a compact space, as I said, you can do this so-called Cul-de-sac line reduction, or not even reduction. You can think of the compact space as various angles, and you can do a Fourier expansion on angles. So you can calculate the theory as just a 5-dimensional theory. And that 5-dimensional theory is dual to our 4-dimensional one. There's another point of view that when you take, to be more rigorous, you have to take this, what I call Penrose diagrams, for AdS5 is a cylinder. Now, if you do this Penrose diagram, you find that the S5 collapses to a point. So for holography, the S5 is not relevant. Okay, so even though the space itself is 10-dimensional, only the 5-dimensional part is relevant.
So my last question is, do we have any hope of extending this conjecture to possibly a DS space-time with 4-dimension?
Well, yeah, I mean that's really what I described. So when I say cosmology, if I said this paradigm includes as a corner the original inflation, and inflation itself is a perturbation around the de Sitter space. You say that the space is approximately the de Sitter, but then suddenly it ends. The de Sitter phase ends. So that is where this idea comes from, and I think there's this kind of sociological question that I ask myself: why is it that people are still not interested in this holographic cosmology? I think the reason is, well, just the historical. People have been trying to first to Vic rotate to the de Sitter, and then they noticed that there are all sorts of problems in defining the AdS-CFT correspondence for the de Sitter itself. So there was that issue. Then Maldacena wrote some papers in which he established a way to describe the duality, but people were still skeptical because of various reasons. But then this approach I'm talking about does not, this phenomenological approach, in some sense, sidesteps the question of de Sitter holography itself, because it's based, as I said, on this D2 brane duality, which is of the type that we understand. The only non-trivial part is still a kind of double Wick rotation, where you turn some space direction to time and some time direction to space. But that is much better defined than for de Sitter itself. So, you know, both Kostas Skanderis and myself have been trying to explain to people all of these points, but somehow people just got their message into their head that, well, doesn't work for de Sitter, whatever that means. So they kind of are not interested yet. I mean, there's very few people that are, well, not very few, but maybe like 20, 30 people that are in the community that are interested in this.
Okay, thank you.
Okay.
Any more questions?
Hi. What's the difference between AdS-CFT correspondence and gauge gravity dualities in general? Because we can find both terms in papers and books. So what's the difference?
So really it amounts to the previous question. So the original, the original duality was derived top-down. Was, well, not derived per se. It's people called, well, motivated if you want. But you started with some well-defined system of D-branes. You took a limit, and you find, therefore, a well-defined relation between two theories. Okay? And that was for AdS space corresponding to conformal field theory, AdS-CFT. Okay? So the original paper of Maldacena gave a standard a set of 4 standard examples. And then people found more of these and so on. But after that, people realized you can generalize further. And at first, they just got rid of supersymmetry, but kept conformal invariance. So it was still AdS-CFT. But then they got rid of even that. And then there was a need to come up with a new term, because it was neither AdS nor CFT. So people used the term gauge gravity duality. Okay, so now when you talk about the set of holographies in general, you call them gauge gravity dualities. But yeah, in the original case, it's still AdS-CFT.
So let's thank Professor Nastase once again. And now we should make a stop for the coffee break, so there should be some refreshments upstairs. Sempre quis falar essa frase, cara.